In chapter 2, we will be talking about strain transformation, and we will concentrate on plane strain condition. Now, complex stresses develop within the airplane wing, for example, here with the longeron and spars. And within the structure itself, we can analyze information or measurement that we get from strain gauge data. So this here is an array of strain gauges. There's two on each arm, one there and one there. So total there's 8 strain gauges, and this arrangement is called a rosette. Okay. So when we do tests on the structure, we will put some sort of strain measuring device, and strain gauges is one form of a device to measure strains. And then we analyze this data, and from the data we can then find the largest normal strain and the largest shear strain, where the strain transformation analysis is similar to stress transformation that we have discussed in chapter 1. Now for this topic, the learning outcome that we expect everyone to be able to do is first is able to analyze strain transformation when the element orientation is changed, and the analysis can be done using equations, strain transformation equations, or Morse circle, similar to what we did in stresses. And another new name that you will be introduced to is called the McClintock strain circle. Now, this McClintock strain circle is an approach to draw the Morse circle directly from strain readings from a rosette. And the other thing you should be able to do is to be able to use the relationship between stresses and strains. In chapter 1, we have done stress analysis. In chapter 2, we are doing strain analysis, and there's a relationship between stresses and strains, and you must be able to use the relationship to get stresses, because you cannot measure stresses in an object. You can measure the load applied, but we can measure strains. So from strain measurement, we do our analysis and we can convert it into stress. Okay, in three-dimensional stress element or strain element, okay, similar to stresses, then we have three normal strain components: strain X, strain Y, and strain Z, and three shear strain components: gamma XY, gamma XZ, and gamma YZ. So we have at the bottom there, on the left is for plane strain condition, all three of them. So in one plane XY, we can see that the first diagram A is for normal strain in the X direction, and the second diagram B is normal strain in the Y direction, and the last diagram C is the shear strain. So the strain components normally for 3D object can change, and they vary depending on the deformation on each face of the element. And similar to stresses, they will change value as well as we change the orientation of the element, as we rotate the element. And as I've mentioned before, strain components at a point are measured using strain gauges in specific or specified direction. For plane strain, similar to stresses, we only consider normal strain in two primary axes and one shear strain component. It's all similar to stresses, and you will find that the final equation that we are going to use will be very similar to stress transformation equations that we have done in chapter 1. Okay, one thing that you need to be careful is with this statement here. It says that plane stress does not necessarily cause plane strain. So when we have a plane stress condition, it does not mean that it will always be plane strain. Most of the time it's not. And the same thing also happens when we have plane strain condition. It does not always mean the stresses are plane stress. And this is due to Poisson effect. If you remember in solid 1, Poisson, so nu is the Poisson's ratio, right? And Poisson nu is del transverse over del longitudinal, right? We take the magnitude of it, and it tells you the relationship between transverse and longitudinal strain, or in this case displacement, right? So when we have displacement, then you can have strain. So Poisson effect will most of the time cause this statement to be true. But it is only for normal strains. For shear stress and shear strain, they are not affected by Poisson's ratio. Therefore, the condition tau xz is equal to tau yz is equal to 0 will require gamma xz is equal to gamma yz is equal to 0. Right? So for shear and relationship between stress and strain in shear, we have tau over gamma is equal to G. Okay? Sign convention as before, we also have sign convention for strains. Normal strains are positive if they cause elongation. Right? So we have two directions for normal strains. We have strain X and strain Y. If they elongate, they are positive. If they cause contraction or if they are due to contraction, reduction in original length, then they are negative. While the shear strain are positive if the interior angle becomes smaller than 90 degrees. So if we look at the first diagram A, the original element is the blue square and the final element is the dotted rhombus or diamond. Okay, so we find that the shear strain in this case is causing the two sides OB and OA to move inwards. In other words, the final angle now, this angle here, okay, is less than 90 degrees because OX and OY is perpendicular or 90 degrees. So the strains cause the angle to reduce in value smaller than 90. And when the angle is smaller than 90, then the shear strains are positive. And again, theta is clockwise. Theta is positive counterclockwise from x-axis, our reference. Similarly for y, when it moves counterclockwise by the same angle, of course, so it is positive theta. let's take a look at the effect of normal and shear strains. Now in diagram A here is before deformation. Before deformation, the length of the size of this rectangle here is given by dx on the bottom or on the x axis, dy on the y-axis, and the diagonal is dx prime, and that is for the rotated axis rotated by theta, and the length is dx prime, right? Where dy is dx prime sine theta and dx is dx prime cos theta. Now, if we have a normal strain x, so let's say we have normal strain here, strain x. Therefore, what happens is the strain will cause an elongation, right? And that elongation is strain x dx, that elongation there. Okay. Now, that elongation has two components. One in the x prime direction and the other one is in the y prime direction. In the x prime direction, the length of that elongation is strain x dx cos theta, and in the y prime direction is strain x dx sine theta. Then if we look at y direction dy, when strain y occurs, only strain y, then we will find the elongation here, right? That is the whole thing is the elongation due to strain y. So strain y dy will give you the whole elongation. Again, it has two components, right? One is in the x prime direction and the other one is in the y prime direction. So we have two components again. Now, if the size dx remains fixed, it doesn't move. If it doesn't move, then we look at shear now, right? If dx do not move, and now we are looking at gamma xy, right? Gamma xy is going to cause dy, that's the original length is until that line there, okay? And dy here will rotate clockwise, or it's going to go inwards. So it's going to rotate clockwise to the last point here, right? So that length there from mathematics, because our angle is very small, so it's gamma xy. So the length there is r, or in our case is dy, times the angle which is gamma xy. So we have gamma xy, dy is that length, horizontal length. Okay. And in the y prime direction is gamma xy dy sine theta. In the x prime direction is gamma xy dy cos theta. Right. So we can find that gamma xy causes the top of the line to be displaced by gamma xy dy to the right. Okay, that's the horizontal line. While in the x prime direction, the elongation is that a component of that elongation, which then becomes gamma xy dy cos theta. If we add all three effects together, the strain x, the strain y, and gamma xy, then we have this equation here, del x prime is equal to strain x dx cos theta plus strain y dy sine theta plus gamma xy dy cos theta. And from our diagram, we know that dx is dx prime cos theta and dy is dx prime sine theta. And normal strain along dx prime is given by this equation here. Okay, and if we replace everything in the first equation on top and rearranging, we will have strain x prime is equal to strain x cos square theta plus strain y sine square theta plus gamma xy sine theta cos theta. Now this equation, if you look carefully, is similar to the stress equation. Okay. Now considering the rotation of line segments dx prime, dy prime. Now if the line dx prime and dy prime rotates inwards, both of them, such that the final shape will be the rhombus shape there. Okay. So it goes in by dy del y prime on that side. So we have alpha angle there. Let's say it's alpha. So we say rotation of line dx prime is given by alpha. And alpha is equal to del y prime over dx prime. Now we can do the same thing for beta, right? And then we can have the equation as shown in this diagram here. So we have equation for beta. Now alpha and beta represent rotation of size dx prime, rotation of dx prime, okay, and dy prime. Now it represents that rotation. So we have the angle as alpha and beta. Now the total will be the strain, okay, shear strain. And since alpha and beta are both in opposite direction, one is counterclockwise for alpha and clockwise for beta. Okay. Therefore, we have the last equation here. Gamma x prime y prime is equal to alpha minus beta because the direction is opposite. Otherwise, we add them up. Okay. And is equal to minus 2 times strain x minus strain y times sine theta cos theta plus gamma xy cos square theta minus sine square theta. Right? And using trigonometric identities, then we can simplify the equations into these last two equations here. Now, if you look here, they are very similar to the stress equations. Okay? So we have strain x prime is equal to epsilon x plus epsilon y over 2 plus epsilon x minus epsilon y over 2 cos 2 theta plus gamma xy over 2 sine 2 theta. And similarly for gamma x prime y prime over 2. So if you look carefully at these two equations and compare them to the stress equations, the only difference apart from changing stress into strains will be this thing here. In our stress equation is tau xy, but in strain is half. Similarly for this one and for this one, right? The rest of the equation are very similar to stress. And these two equations are very powerful, similar to the stress equation. We can find values of normal strains and shear strains on any plane, any direction. Now you notice that I purposely do not put strain y prime equation here because you don't need to similar to stress. You just change the angle theta. For y prime, you just add 90 degrees. Okay. Now those are our equations, right? Now this is the shear strain equation. The shear strain equation gives normal strain and shear strain in the x prime direction and y prime direction. and the shear is in the x prime y prime plane. Okay, it's as shown in the right here with the two diagrams A and B. Now the first equation gives you the first diagram A, and the gamma x prime y prime equation will give you diagram B. Right? Okay, principal strain, again similar to stresses, we also can do the analysis for the strain. I'm not deriving the equation here because it's quite similar to stress. The only difference is gamma. Okay, so if you notice that tangent to theta p, the only difference is here again. In our stress equation is 2 tau xy. In strain is just gamma xy. Similarly for the principal strain equation, strain 1, 2 or strain max and min. The first part is same, similar to stress. The second part here is also similar, only here we have the difference. Because in strain, we have to divide by 2. Okay? And maximum in plane shear strain, similarly, we can have this equation here, or you don't have to memorize that and just add 45 degrees, right? And maximum in plane shear strain is given by the square root of the previous equation. And again, remember when we have maximum in plane shear strain, we will have average normal strain. So it's still similar to the stresses. Let's take a look at an example, but this is for the basic equation first, not for principal strains. So this is an example from your textbook. It says here, a differential element of material at a point is subjected to a state of plane strain. Strain X is 500 microns. The unit for strain, remember, is very small, so it's times 10 power minus 6. So we have microns. It doesn't have exact unit meters or millimeters because it's a ratio. Del over original length, right? It's still the same unit. Epsilon y is minus 300 microns and gamma xy is 200 microns. So what we have is strain X is 500 and microns. Normally we write something like that using mu, right? The Greek letter. Strain Y is minus 300 microns and gamma XY is 200 microns. Okay, it's mu. Now it says determine the equivalent strains acting on an element oriented at a point clockwise 30 degrees from the original position. Not diagram A, but is rotated 30 degrees clockwise. So our reference is always X, right? Or Y. In this case, we are using X as a reference. Now X prime will be clockwise 30 degrees, or in our case, when theta is clockwise, it is negative. And for Y prime, we just add 90 degrees, so we have theta for Y prime. Okay, this is for Y prime. So we use our basic equation. Strain X prime is equal to this equation here, and you just replace strain X is 500, strain Y is minus 300, right? The only thing is micron, so times 10 power minus 6. Okay, plus strain x minus strain y. So it's minus negative 300 over 2 times cos 2 theta. So theta is minus 30. So times 2. The angle is 2 times. And then plus gamma xy over 2. So gamma xy given in the equation in the question is 200 microns. So it's 200 over 2. Don't forget this 2 here. Okay. And sine 2 times the angle. So the angle is still negative 30. So we just times the angle. And that will give us the normal strain in the x prime direction. And for the shear strain, we just use this equation here. Gamma x prime y prime over 2 is equal to negative of strain x minus strain y over 2 sine 2 theta plus gamma xy over 2 cos 2 theta. Replacing all the values for strain x, strain y, and gamma xy, and also theta is minus 30 degrees, we will get this answer there. Gamma x prime y prime is equal to 793 microns. Right? For the y direction, as I've said before, you do not need to memorize a special equation for y. You just change the angle. So then theta is now is 60 degrees. Okay, theta is 60 degrees instead of 30 degrees clockwise. It is going counterclockwise. And so we can get strain x prime is a negative value, meaning the x prime side will be contracting. So you have a contraction over there by an amount. Okay.